Okay, let's look at another example for how to handle equilibrium calculations. This time we'll use the solver when k is mid-range and no simplification with a small x assumption is possible. So this is a good time to use the solver when we don't have a way to simplify. First of all, we choose x to be as small as we can get it. So we always select the x to go in the spot in our rice table that makes it as small as we can get it. And if we can't simplify, then you have to use the quadratic equation. Luckily, your calculator can handle that math and you don't have to fumble around trying to remember the quadratic equation, because that's not the point of chemistry. We want to be able to use math as a tool, not have it be an obstacle. So here's a reaction that you saw before. H2 plus I2 makes HI. And now that we're at a different temperature, my equilibrium constant is different, 38.6 now. So it's neither high nor low. We need to know the equilibrium concentrations if 1.8 moles of hydrogen in a 2-liter container is mixed with 1.6 moles of iodine in a 2-liter container, and the 2.6 moles of HI are mixed in the same 2-liter container. So pay attention, because moles per liter gives us molarity. So I have 0.6 molar H2 and 0.8 molar, oh wow, that's 0.9. I'm losing my mind. Okay, 0.9 molar hydrogen, 0.8 molar iodine, and 1.3 molar HI, all mixed together. So let's put this into our rice table. First, we'll write our balanced equation. Hydrogen plus iodine gives us hydrogen iodide. 2 of those, in fact. And then I don't need to write numbers in this column. Let's put our Kc, since I have molar concentrations. Hi is squared, and that's over hydrogen to the first power and iodine also raised to the first power. Great. Now we calculated the molar concentrations earlier. So I had 0.9 molar H2, 0.8 molar I2, and 1.3 molar HI. We're going to lose some of my hydrogen and lose some of my iodine and gain twice as much HI because the stoichiometry says so. It's a 1 to 2 mole ratio, right? That's straight from our balanced equation. Now let's add the equilibrium is going to be initial plus change. So I get 0.9 minus x, and I get 0.8 minus x, and I have 1.3 plus 2 times x. And we have an equilibrium value equal to 38.6. I'm going to put my products over the reactants. So 1.3 plus 2x goes up top, and that gets squared, divided by 0.9 minus x times 0.8 minus x. The problem is, with this value of 38.6, we can't safely assume that the value of x is going to be really small. And so I couldn't say 1.3 plus 2x is essentially the same as 1.3. That's not a valid assumption anymore because my k is too big. So we're going to put this in the solver, in your calculator. Alright, so first let me rearrange so that I multiply the denominator across. So multiply this over here, and I get 38.6 times 0.9 minus x times 0.8 minus x. And I still need to have 0 on the other side. Right now I got this over there. So subtract this across, minus 1.3 parentheses plus 2x parentheses squared. Now I'm all equal to 0, and I can put it in my solver. Great, let's give that a try. So remember, go to Math, and then find the function that is your solver. And let me clear that out. So we had, oh dear, I want to look at it while I do it. So 38.6 parentheses 0.9 minus my variable x parentheses and another parentheses 0.8 minus my variable x minus parentheses 1.3 plus 2 times my variable x, but that quantity is squared, and that's going to be equal to 0, which is already there. And for x, what should we guess? We know it's bound to be some significant amount. Anything between 0.1 and 1 is probably okay. I'm just going to go with 0.1. Why not? And then I do alpha solve. Hey, there you go. So it is a value between 0.1 and 1. It's almost halfway in between. So we see the value of x is 0.48, and let's work out the rest. So if x is equal to 0.48 molar, then I know my concentration of hydrogen is equal to 0.9 minus 0.48, and I'm going to let my solver do this math. So quit out of the solver, and we want to take 0.9 minus x, my variable x. And then enter 0.417. Whoops. We'll call that 0.42 molar. And then my iodine concentration, I2, is 0.8 minus x. And I can let my calculator handle that one too. So 0.8 minus variable x, enter, 0.32 molar, that makes sense. And then concentration of HI, sorry, I have to squish this all in, is 1.3 plus 2 times x. Let's let our calculator handle that too. 1.3 plus 2 times the variable x, 2.26, so 2.3? Yeah, 2.3 molar. And we're done. We got the calculations of the concentrations of all of our substances at equilibrium using our solver on the calculator for a value of K that is in the middle range. So it's not so bad. Remember, rice tables are your friend, but don't get caught up in solving rice tables when you don't need to. In class, we'll practice some of those situations where just looking at the equilibrium expression will get you the answers you need. Great, so I will talk to you all soon.